Let's begin with an example of superposition in the frequency domain. And this time, we're going to have all of the sources be at the same frequency. So our two sources are both voltage sources. They don't have to be both voltage sources, but they do have to have the same frequencies. And to use our concept of superposition here, we'll analyze it firstly, just keeping this one on and turning this to zero. So a zero voltage source is a short. If it was a current source, it would be an open. And in the frequency domain, our source looks like this. And we need to figure out what that impedance is of our capacitor. So we'll write that right underneath it. Z sub C is equal to 1 over J omega C. Our omega is 10. Our capacitance is 1/10. So that's 1 over J. And we can multiply top and bottom by J. So we get J over J squared. J squared is -1, and this whole thing becomes just minus J. And this is the voltage we want to find. I'll call it capital V since we're in the frequency domain. You could use the voltage divider equation and say that's equal to 4 at an angle of 90 times the one you want to find over the sum. But it's a whole lot more simple to just say these two impedances are the same. So they'll both drop the same amount of voltage. And so they'll both drop 2 at an angle of 90. And that is our partial voltage for this first circuit. Let's do the same thing for our next. Now we've got this thing shorted. I'm just going to move this impedance off to the left, give us a little bit more room. Same impedance here, 1/10 farad, same frequency. So this will still look like a minus J. And now we've got a minus J over here. This is 12 at an angle of 0. 12 at an angle of 0 is just a fancy way of saying 12. Right? You can see that from our complex plane. Here's the real part. Here's the imaginary part. If we write 12 at an angle of 0, that's just the same thing as writing 12. And we want to find this voltage. Maybe I should call this V sub 1 and this V sub 2. Now, this is the same, though, as the voltage across this capacitor. So once again, it's the exact same voltage divider. It's 12 times minus J over the sum. And since these are the same, we can do this mathematically, or just more simply, say the 6 is divided into half drop by this guy and half drop by its identical one. And so here's our second partial voltage. And now we can say our full voltage is equal to the sum of the partials, 2 at an angle of 90 plus 6. You can throw that in your calculator right away, but I think it's easier to firstly convert this 2 at an angle of 90 into a rectangular notation number. It's 2 away from the origin, so it's somewhere in this circle, and it's at an angle of 90, so it's up here. So this is just a complex way of writing J2 plus 6, which when you put in your calculator is 6.32 at an angle of 18. Again, there's nothing magical there. You could do that by hand with a little bit of trig. You could say J2 plus 6 is this point right here. And that is a Pythagoras' theorem that's equal to the square root of 6 squared plus 2 squared away from the origin, which is 6.32. And you can figure out what its angle is using inverse tangent of 6 over 2, which gives you the 18. Armed with this, we can find that the entire voltage is 6.32 cosine of whatever that constant frequency is, which is 10t plus 18, and that's in volts. And that's how you use superposition to solve a relatively difficult circuit in a fairly easy manner.